title tells you what we'll be talking about here. Okay, so first, let's get started. I guess as we all know, lots of real mathematics is getting formalized in real time, getting back before the referee had even had time to digest the papers. So this is a really dramatic development that I think no one was expecting, say, 10 years ago. Now, everyone knows about formalisms based on the calculus of construction, which is, of course, why I'm not going to talk about them. So, I do want to say, by the way, I learned about dependent types from De Bruyne in person when I was 21. So I'm not speaking from a background of ignorance here. Actually, I was there at the birth of the calculus of constructions. I've done a lot of work on Martin-Love type theory as well. Just a remark. Now, a very important question, is all mathematics formalizable? So, I like this quote, we do not have a workable definition of the word mathematics. And I think Kevin Buzzard was talking about this a moment ago, how a mathematician goes into a kind of meta-language knowing what is true and using the fact that it is true. And then the question is, how can we formalize this? And I think it's impressive that De Bruyne was aware of this issue in 1968 before anything much had been, I don't even think they formalized the construction of the real numbers in 1968. But of course, De Bruyne was a proper mathematician who worked in many fields and has his name on the De Bruyne, sorry, he has a Earth number of 0 and so on. Right, so.
That explains a lot.
No one have 0 except Earths. Oh, I see. Yeah, then it's 1. Right. Mine is 4 or something. Anyway, so let's see. How do we do things in Isabelle? Well, oh wait, it went. I skipped a slide. We had a bunch of stuff. I'm talking about 2017, which is when my EU-funded Alexandria thing started. Wait, did I skip 2 slides? It's not working right. Sorry, I don't understand. Let's go back. I'm very sorry about this. So, in 2017, I got a lot of money from the EU. With the aim of trying to use tools that we had developed mostly to support computer science and used it to support mathematics instead. And the question was, as it shows in red, what can we formalize as regards mathematics? What kinds of proofs and proof styles can we formalize? And we had already a lot of mathematics formalized in Isabelle. I mean, originally, reasoned computer scientists were formalizing mathematics because they needed to do something involving floating point arithmetic or something, and then they started doing it because it was a lot of fun. So there was a lot of stuff done, probably most of it by Manuel Libero. A lot of stuff was done, but the question, and of course I have to give Kevin credit here for pushing us and saying, come on, you need to go deeper and harder, and this is sounding a bit dodgy, but anyway, we need to really push our boundaries, and also we have to compete with the type theory world where tons of amazing stuff was happening. So we got our money from the EU, and we got started. And here are some of the first things we did, and I'm glad Angeliki is here somewhere because Angeliki worked on this stuff with irrational rapidly converging theories. Anthony Borg did the projective geometry stuff, and Wendell, I shall tell you how these guys are at the end. We did a bunch of fairly basic early experiments trying to look at some recent and important material. Well, there's another thing, this was supervised by Anthony Borg as well. This is how you can extend an arbitrary field to be algebraically closed. And this is an interesting example. You see, looking at that thing in the middle, and I would have thought this is like a very canonical example of a thing that needs dependent types, because you start with a field and you extend it with an arbitrary number of further fields until you get the final field you want. And I think Anthony was very clever at taking these two interns we had, and all of them had experience, and Anthony had a lot of HOTT knowledge as well, and saying, formalize this, guys. And they did it. Now, their paper shows that they're kind of coming from the type theory world and saying, how can we do this without dependent types? How are we doing that? And kind of, in some ways, doing things that now in retrospect look silly. So they wanted to make a product of groups, like an arbitrary n-array product of groups, did something involving, I've got a list of groups and I want to make a product, and they got into some trouble with dependent type, which they fixed in a very clever way, not coming back to it years later and saying, there is no connection whatever between lists and the product of groups. And if you did the textbook definition just literally out of a textbook, you would have got the product of groups directly, and you wouldn't have had any struggle with the fact that when you do recursion of the list, the types don't match up. Because there aren't any lists, and there shouldn't be any lists, and their index set could be uncountable. Anyway, I talked too much. You see, I have to follow from Kevin here. So then, as we carried on, we did more stuff. So the irrationality thing we extended with a further paper. And then with Myrna here, and with Angeliki, we did some cool stuff on ordinal partition theory. I will say this, Kevin, that reading the set theory stuff, I think there's a lot less mumbo-jumbo about canonicity and so on. And I think in that particular paper by Jean Larson, there was, I would say, what I would call an off by one error. One place where she said, this is obviously so-and-so, and it took me 2 weeks to prove it. And the rest was pretty straightforward, I think. And we did, we threw together a formalization of schemes, not that we needed it, but we were just trying to get back to Kevin. I don't actually know that we did it in a very good way. It was more showing that it could be done. I think if you really wanted to use it, you would go back and refine it and do it try and do it in the best possible way. But whatever. And the thing that's nice is that there were 6 papers published, and we had 3 of them. The other 3 were using lean. And I think there was another formalization of schemes in there, and then the others, I don't know. So we had to do some more, and whose idea, was it yours, Angeliki, to do extremal graph theory? Yeah, Shemeretti regularity lemma, and I think you chose the additive combinatorics as well. My student who chose combinatorial block designs, and probably manually Burrell and Wenda chose to try and formalize number theory, and Anthony doing omega cat. So Anthony was really, coming from the HOTT world, he was really quite fixated on seeing how far you could go with simple types. Now, I'm not sure if I should go into much detail on what this mathematics is. So if you know it, then you're not going to learn any more from me. And if you don't know it, you're probably still not going to know it. Let me just say, this is apparently a very important theorem, and more importantly than the theorem, it's a very important new conception in mathematics of having these big graphs, having this notion of uniformity, this notion of an epsilon regular partition. And then you prove this result, and the actual proof is not that complicated once you figure out what the subset symbol means. And finally, then we applied it to a thing by Roth, not the famous Roth theorem, but a simpler theorem about short arithmetic progressions. And all of this is regarded as non-trivial mathematics, so we thought this is, again, showing we can do real mathematics, which is the point of the exercise. we went on to this thing. Now, additive combinatorics is the bee's knees now, right? Everyone is really excited about it, combines all these things together, and it's dealing with I think I can explain this. So it's dealing with some sets. So if you've got a set A and a set B, and you imagine every way of adding up elements, an element from A and an element from B, that is the sum set. And the only thing that makes it a bit sexier is they're not necessarily integers, but they're any abelian group written with a plus sign. And then the iterated sum set is when it's one single set A that you're adding up n times. And then it turns out there's all kinds of things that then people want to prove about these. I worked on this one. That doesn't mean I understand it. And apparently this last one is really regarded as an important result. And I think it was there a best paper award or something? Or, no, it was, Chelsea got the best paper award. I think this was a runner-up actually, but it was a runner-up in a way that doesn't get announced, which is unfortunate. Right. I must mention the work of my student Chelsea. She was mad enough to want to do this before I even had funding. She just thought combinatorial block designs were cool. Now, I don't think there are many people who think that. Or anyone here who thinks combinatorial? I see, there's some, okay. And what she did, now she used locales. And the thing about locales is you can set up, I think she has a massive locale hierarchy that fills up an entire slide because there are so many zillions of ways of combining different conditions together. And I mean, it would be self-parody to say the names of these different block designs that have all these different attributes or don't. And you do have to know which exact crazy combination of things you're working in at this particular moment, because that determines what axioms you're allowed to use at this particular moment. Anyway, she formalized, as I said, she came up with a very elegant design for dealing with all these different kinds of block designs for inheriting things in the right way, and then she proved various results. The other cool thing she did, and this was what I always thought of as a horror, so I always said in any mathematical proof, if someone now says, imagine coloring edges red and blue with probability p and 1 minus p, it's time to tear your hair out. Unfortunately, you find these things, and so Chelsea finally got to grips with this and said, yes, here's how you do it. You set up a probability space, and you do this and this and this, and you show the probability of the set is greater than 0, and bingo, the set is non-empty. And the constructivists will hate you, and that's their business. Okay. So I wanted to go through some of the papers we formalized. Right, so that's the irrational convergent series. This one's for the partition, so again I have to thank Myrna and Angeliki. The cool thing about this paper is it's a 5-page paper with a 3-page paper of errata. Yeah, this stuff is quite gruesome, and this is set theory, right? And this one, which has no errata to speak of, beautiful work, but I think probably it's like Gödel apparently had almost a mental breakdown after proving the relative consistency of the generalized continuum hypothesis. No, I don't know how Jean survived doing this, because again, this is incredibly technical work. Anyway, moving on. Angeliki wanted to do some of Gowers' things. I believe this is probably taught to undergraduates, or is this graduate level?
I think it is part 3 of tripods. So
Part 3. So it is,
Masters.
technically, part 3 is undergraduate, but it's very advanced.
it's master level yet.
It's fourth year, but yeah, it's very advanced. So I think we did most of the stuff in the red box, I believe. Okay. And then for my sins, I thought I would tackle this thing. Now, for those who don't know, so about a year and a bit ago, this paper came out. Apparently, it's a landmark results because they've got this Ramsey base of the exponent down by a very small exponent. So the meat of this work is in the first 12 sections, and just last week I finished section 11. I'm feeling pretty brutalized by it, actually, because
There are only 1 to 10 and 12 to go.
I did that 1 to 10 as well, but 12 to go. Now, I will admit, I cheated because Bobix was available, Bobix formalization in Lean, and I wouldn't have even considered this without there being Bobix in Lean, because I wouldn't have thought I had any chance. But I did occasionally cheat by looking at Bobik to say, like, is that a floor or a ceiling? Because the authors never bothered to specify. I couldn't really use much of his proofs because I couldn't make any sense of them. But occasionally I would see a function or I would see a property and say, hey, it would be cool if I proved that, because then I would be able to do such and such. So I did certainly benefit from Bobik's being available. And I think I would have probably given up around section 2 if Bobix hadn't been available. But my version, which I said, it's up to the end of section 11, is my own. Where I have copied ideas from him, I have indicated. And I have to say, for someone who's constantly getting their inequalities the wrong way around, it is useful to have something with enough automation that it's a typically, if you've got the inequality the wrong way around, and when you're trying to prove it, you find it's been replaced by an equal sign, and then you say, oh fuck. And it's cool that it does that. Okay, so what did we learn? And I think the coolest thing, and I think one of the differences between, one of the surprising facts about mathematics is that they talk about specialities like number theory or combinatorics or so on. But these are kind of convenient for bureaucrats, but there are really no boundaries. And I found it stunning, the extent to which at any point, anywhere, you might need anything. And that could be seen as a real obstacle to working, but it's not. We were trying to find out what we couldn't do. Now, I must admit, we didn't try the hardest thing because none of us know. I mean, I have no idea what a scheme is, even having taken part in the formalization. All I know is you start with rings or something and you just pile stuff on forever. And the interesting thing in terms of set theory is that you're hardly going up in the cumulative hierarchy of sets. You're hardly going up at all. So you're piling mountains of definitions on, but you are not actually shooting up in terms of what a set theorist would regard as real complexity. That is not happening. And even like the fixed point of the Aleph operator is still a relatively smallish cardinal. I mean, it's not a large cardinal. So the fixed, sorry, I'm getting a digression here, but you know the Aleph thing, right? Aleph 1 is counted. So there is a thing which is its own fixed point. So Aleph of Aleph of Aleph of Aleph of Aleph. You would think it's kind of a big cardinal, right? But it's not technically a large cardinal. And the proof that it is there is actually almost trivial. Sorry, I got distracted. We have good performance on the computer, so we are seldom waiting around and getting frustrated. We have automation so that thickos like me who's saying, is this true? And I'm thinking, God, it's true. Why is it true? I have no idea. I'm not interested. Actually, I mean, there is a danger there. And I have to warn you, if you're starting to use Isabelle, and especially if you have a view, sorry, to streamline your path, to get rid of some obvious things and get on with it. And if everything is starting to be proved with the same proof, then you better go back and look at the things you assumed, because it's found a contradiction there. Sometimes it will even tell you, it will actually say, excuse me, your assumptions are already contradictory. And that is a useful thing to know. And I think a lot of the things we do count as modern maths. And the thing I would really like to push as well is our proofs are kind of legible. So what do I mean? I want to exemplify these a bit. So In terms of no borders, this is the header of the modular functions development, which is finally, part of this is finished and is going to appear at ITP in Tbilisi, which I'm sure will be a lot of fun. If you've not been to Tbilisi before, it is worth it. So we haven't had any problem bringing in all that stuff to do something else. I did a weird thing for Kikim where I did an example by Erdős involving transfinite recursion, the continuum hypothesis, and something to do with sets of holomorphic functions, all in a weird little example that Erdős had stumbled across. I mentioned the probabilistic proof. In fact, I had to do a couple of these for this Ramsey paper I mentioned. And yes, the locales allow you to construct things in multiple ways and inherit them, and you don't get a problem with diamond issues here. So about performance, so yes, the whole Shemeretti development runs in 14 seconds. I don't know why the Roths is so long. So anyway, so it runs fast. Now I want to say something about the legibility of proofs, because I believe I still have time. And I saw this somewhere, I can't remember where I saw it, and is Andrew Granville here?
No.
Okay, he's one of the lean people.
No.
So the question is...
He's one of our main critics.
Oh, I see, sorry. Okay, well then this is proof he's one of the main critics. There is, I mean, I know from, I'm old enough to hear, echoing back to my undergraduate days, the loathing that at least some mathematicians have for computers. And okay, you don't have to trust them. We don't trust them. You maybe heard of the Horizon scandal in the UK where loads of postmasters were sent to prison because somebody believed a computer system more than they would believe some person, often Asian, running a post office, where it was easier to believe all these people were crooks than to believe there were bugs in their program. So for some reason, I mean, you are right not to trust computers. So the point is, we would like to be able to read the proof itself and say, fuck the computer. So this is a really simple example. It's a thing about distributing the summation over subtraction. Now, I know if you don't know Isabelle, this is not at all easy to read, and yet you can see in there are some assertions. The first line, there's some simple fact about natural numbers. The second line there is something about sets, and the syntax for sets of ranges of integers, but that's not so complicated. We prove a certain function is injective, and you know, we are working through, and you can say, okay, I don't trust your computer, but that derivation looks okay. Now, for my second example, and I suppose everyone knows Ramsey's theorem, but if you've kind of forgotten, is an example here where you have 6 people at a party, and if you have anytime you have 6 people at a party, you are guaranteed that there are either 3 people who all know each other or 3 people who all don't know each other. So the people who all know each other is called a clique, and the ones who don't is called an anti-clique. And there you have an example where, yes, there's an anti-clique in blue, and in fact I haven't even colored in all the edges. So, I'm not even sure you can draw another edge without making more cliques or something. So I have an example that a very simple example is that the Ramsey number for n plus 1 and n plus 1 is greater than m times n, which is to say it is possible to have a party with m times n people without a clique or anti-clique of the specified sizes. So how do you do it? And this, actually I stole this proof from Bovik's development actually, though I imagine it's fairly well known. So you construct this m by n graph, and then to prove the theorem we have to show there are no cliques and no independent sets, and the graph looks like this. So, and by the way, you have to assume where the red lines are that every point is connected to every other, not just the adjacent one. Now, if you can see there that along, let's say the horizontal is m, then clearly there is no m plus 1, right? And vertically it's n, And of course, to have them unconnected, you have to go up a level every time. Obviously, there's no n+1. And if you want a big critique of formalized proof, is that this should be the end of proof QED. And of course, that's not how it works. However, this is not too bad. So this is the proof. And what you can see, there are the two cases. So if you want to assume for contradiction that a clique, that it is a Ramsey number, then you choose an arbitrary graph. Then you choose your particular coloring that I gave you, and you say, okay, there's either a clique or an anti-clique. You have two cases, case 1 and case 2, and in each of the cases, you can see I'm constructing something. I'm showing that the cardinality is less than n, therefore it is not an n+1 clique. The argument is there, and again, I would say that is a tolerably legible thing. Third example. So this is a page from a Paulson's book on modular forms or something. Now this particular theorem is not very difficult. So it's a way, it gives you a fact about approximating a real number by a pair of integers subject to the conditions shown there. And it's a pretty elementary proof by the pigeonhole principle. So you can see you're choosing n+1 real numbers there, and you're subdividing the interval from 0 to 1 into n intervals. Therefore, by the pigeonhole principle, there will be 2 of those inside one of the subintervals, and then you do some calculations and you're finished. So that kind of proof, this is half of the formal. But you can see, again, you can say, okay, I'm defining. One of those is the set of all the fractional parts that was shown in the text. Then the set Y is the subintervals of the thing from 0 to 1. And then we start showing this is injective, blah, 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 that's finite. And then you have F as a function from X to Y, and then we can prove by the pigeonhole principle that that function is not injective. And then you have the calculations, and that's the rest of the proof. So again, I think we can claim that this is a tolerably legible formalization. So what is the point? I think it is nicer, but also I think there is a trust barrier that this really helps to overcome. And also you can come back to it. So like I'm doing this diagonal Ramsey thing, not to say it's been formalized, look, it's done. Because Babak's done it, it's already formalized, it's done. What I would like to say, and if you've looked at this diagonal thing, I think it is a mathematical equivalent of a Rube Goldberg machine. So it's got zillions and zillions complicated things and zillions of arbitrary constants. It's be begging to be refined, to be optimized, to be strengthened by tweaking this and that. And with the development I have, I would like to think that someone could say, you know, what happens if we change this? Run it through, where will it die? Ah, yeah, what can we do about that? And I think that for tinkering with this and strengthening the result, people might want to use a thing like this. Anyway, I'm always showing these quotes because I think I used to have them pinned up. So Heiting, one of the founders of intuitionism, no system of formalism, no system of formulas could ever capture the human mind. I agree with him, actually. And Gödel saying the same thing in a more technical way. It is impossible to formalize all of mathematics in a single formal system. By the way, this is not in his incompleteness paper. It's actually in a book review. Which I stumbled across at random. The amazing thing is that we did all this stuff in simple type theory, and if you know your set theory, you know that simple type theory lives in a tiny, tiny part of set theory. Simple type theory is a very small mathematical world. And I think it's an interesting, I would say it's an observation that almost the whole of mathematics that it's actually done, and with the exception of set theory itself, actually lives in this very small world. So, as I said, everything we tried seemed to go. Now, we have been working, so this formalization of the book on modular forms is about half the chapters done. But people have got other things. The manual has been doing the harder stuff, and it takes time. I've constantly struggled, and of course it's my fault that the not knowing that the subset symbol can mean almost anything. Not understanding that a degenerate case is just not going to be mentioned even if it requires some systematic changes in a bunch of places. Actually, a big drawback, a big limitation, and really unavoidable in Isabelle HOL, the axiom of choice is there, right? If you don't like it, tough. Okay, now what really is causing problems for us? It's just so big. This is like, Henry V tried to conquer France, in the 15th century. And the trouble is there's too much of it. If it had been a bit smaller, he'd have been fine. Now, I know there's going to be another whole workshop on organizing library. Now, the funny thing is, Mathlib and Isabelle's thing, which is called the Archive of Formal Proofs, are done on an entirely different principle. So the Mathlib has a very strict organizing principle, and the AFP has no organizing principle at all. So this is why we might have 5 different treatments of, I don't know, matrices or something. And you just have to pick the one you want. And then, yes, finding stuff is a problem anyway. And as I mentioned before, proving obvious things, I think, especially if you are a mathematician and you think, a horse is set as finite, for God's sake. Because you set all those things to 0, and so you have all these different things, but they're all equal to 0, and therefore the set of them is finite, right? That was addressed to Kevin. Whatever it is, I think it gets really, really frustrating when a thing that is obvious is suddenly forcing you to take hours. And this is why we have sorry, and it does allow you to push forward. I don't trust myself enough to use sorry very much because my intuitions aren't very good, and I'm always, as I said, getting the inequality the wrong way around or something. The main purpose of sorry is really, for me at least, to go one step ahead. Say, if I could prove this lemma, would it help me with the next one? And often I find it doesn't help me because, in fact, the original lemma was wrong because I had the inequality the wrong way around. And then when I finally fix it, maybe it even does work. But yeah, this is going to be a thing, I think, for the adoption of this among general mathematicians. This is probably number 1. Anyway, I'm going to finish up. So I should thank some of these people. Now, Angeliki is actually here. I don't think anyone else is here. And I can thank Myrna as well for putting us onto ordinal partitions. And of course, I have to thank the people who gave us the money. And that's it from me.